if you were told you had a gram of cobalt, a gram of carbon, and a gram of lead, which one would have the most atoms in it, or would they all be the same? What do you think? You really should be thinking in terms of moles, which was our point of yesterday's lesson. You know, if you look at the masses on these things, cobalt has a mass of 59, carbon has a mass of 12, and lead has a mass of 207. So we're talking grams per mole for each of these. Now that you know these atoms have these different masses, is your answer the same? Okay, hopefully you're thinking carbon would have the most atoms because it's the lightest mass, so a gram of carbon yields more atoms for you than a gram of the others. So now let's get into empirical formulas. That's a fancy name. Okay, empirical means by experiment. We have two pictures here that illustrate what we're going to do today. If you have a compound made with lead, chromium, and oxygen, there's a percent mass by way of the ratio of these atoms in the compound, or oxygen, nickel, hydrogen, carbon. We're going to work up to the fact, if we're given the percent by mass, that we could derive the formula for the compound. That's our goal for today, but first we have to do some groundwork. Let's first look at the simple example. If you had a clover, we would recognize that for every clover I have 3 leaves. 3 leaves constitute the clover. You could do the same thing with every spider having 8 legs, so if I have 4 spiders, I'd have 32 legs, or chairs, if I had 5 chairs, I would have 20 legs. If I have a phosphoric acid molecule, because it's composed of 3 hydrogens, 1 phosphorus, and 4 oxygens, my mass percent for phosphoric acid is going to be different for the type of atom that I have, because these atoms have different masses. Okay, you recognize that hydrogen has a mass of 1 and phosphorus has a mass of 31, and each oxygen has a mass of 16. My overall mass is the sum of these. So my overall mass turns out to be 98 grams per mole. So if I look at my mass percent hydrogen, it would be 3 over 98. And my percent phosphorus would be 31 over 98. And my percent oxygen would be 64 out of 98. And these will all sum up to be 100% because there's nothing else left. If you do this math, this turns out to be 3%. This turns out to be 32%. And this turns out to be 65%. Yes, indeed, it adds up to 100%. If you had a molecule of carbon tetrachloride, carbon's worth 12, each chlorine's worth 35.5, 142 for the masses of the chlorines, plus 12 more would be 154 grams per mole. If I want to look at the percent by mass of chlorine, it would be 142. This times 4 is 142. Divided by 154, it would be 92% chlorine. In general, what you see me doing is that the mass percent of any element is the mass of just that element over the total mass of the sample. I'd like you to pause this slide and do 2 calculations on your own and make sure that you can do this. I have the formula here at the top, and what is the mass percent of sulfur in H2SO4, also known as, I hope you can say, sulfuric acid? And then do this one. What is the mass percent of chlorine in C2Cl4F2, which is a chlorofluorocarbon, also known as Freon 114, one of the banned chlorofluorocarbons that ruins the ozone layer. So pause this, do these calculations, and I'll come back with the answer. Okay, so hopefully you figured the molar mass on this is 98. And so sulfur's worth 32. 32 over 98, you should have gotten 33% sulfur. And when you did the molar mass on this guy, hopefully you came up with 204 grams per mole. And the chlorines are the majority of it. 142 over 204 should have been the chlorine mass. And so you should have computed that it's 70% chlorine. Now you might have had 69.4% and so you called it 69. I don't worry about that. Our math is the same. It's just rounding differences and who carries memory in their calculator and who types it in fresh. Alright, so now we're going to reverse what we're doing, and you're going to be given the mass percent data, and from this you're going to derive the empirical formula for the compound. This is truly investigative work. You're going to do this experiment on Friday. This is acting like a real chemist. You're getting to have enough foundation that you can do some real chemistry in the lab. So you're going to figure out the mass percent data, and from that figure out what this compound is. Pretty interesting, huh? So just to define, once again, the empirical formula means we do some experiments, and from that we determine masses, and from that we can come up with the formula, like H3PO4. For example, it is possible to split water, and you can get the masses of the gases inside of them. Let's say that you did this experiment, you split water using a battery, and you were able to get the masses of these gases, and you figured out that you had 3 grams of hydrogen and 24 grams of oxygen at the end of that experiment. How would you figure out the formula? Well, hydrogen and oxygen have different masses. 3 grams of H, that's a 3, believe it or not, divided by 1 gram of hydrogen per mole would say I have 3 moles of H. I need to get into count and correct for the fact that these atoms have different masses. In a mole, I'd figure out that I have 1.5 moles of oxygen. So I'm now down to mole count, which is those subscripts I'm looking for. The way we do this is we divide by the little guy, and you'll come up with whole numbers that become the subscripts. This is how I figure out I've got 2 H's for every oxygen. Here's a stepwise sequence. The first thing we do is we assume we have 100 grams of sample. That's if you're given percent data. I was actually given grams data in that last example. We then convert to moles by using their molar masses off the periodic table. Some cases you're not done yet, you don't get whole numbers, and you need to clean it up. You come up with this pseudo formula for a compound. The pseudo formula in the last example would have been when I had H3O1.5. I then divide all the subscripts by the smallest subscript. I divide it by 1.5 to come up with a cleaned up version of H2O. Here's an example saying that we take titanium, we react it in the air, it forms 5.4 grams of a metal oxide. It's titanium oxide. But we don't know how many oxygens combine with the titanium, and that's what this data will determine for us. So the molar mass on titanium, if you look it up on the board, you'll see that titanium has a mass of 48 grams per mole. So we can figure we have 0.0675 moles of titanium. The other thing in this compound is the oxygen. I don't quite have my oxygen grams. I need to subtract these two and figure out how many of the grams are due to oxygen, and you get 2.16 grams of oxygen. So I'm going to convert that to moles. 16 grams per mole. And I'm going to get 0.135 moles of oxygen. Our next step is to divide by the little guy, and I'll get 1. Divide by the little guy, and I'll get 2. So I come up with my empirical formula being TiO2, titanium 4 oxide. I'd now like to switch and work the problems on your worksheet. I'll do 2 examples and you take it from there. A compound is 24.7% calcium, 1.2% hydrogen, 14.8% carbon, and 59.3% oxygen by mass. Write the empirical formula and name the compound. Okay, following our stepwise sequence, our first step is to assume you have 100 grams of the compound. If I have 100 grams of compound, then I have 24.7 grams of calcium, and I have 1.2 grams of H, and I have 14.8 grams of carbon, and I have 59.3 grams of oxygen. Our second step in the process is to divide by the molar mass of each of these. Calcium has a mass of 40. You get 0.6175 moles of calcium. You see how your units work out? My grams will cancel and my moles will flip to the top. It's really easy to do this next one. You divide by 1, you get 1.2 moles of hydrogen. I divide by the molar mass of 12 grams per mole for carbon, and I get 1.233 moles of carbon. And I divide by the molar mass of oxygen, which is 16, and I get 3.71 moles of oxygen. Alright, my pseudo formula that I would have at this point would be, writing over here, Ca 0.6175, H 1.2, carbon 1.2, oxygen 3.7. Okay, we never see formulas like that. We need to convert it to whole number. Our next step is to divide by the smallest one, which is this 0.6175. We get 1. 0.6175, we get 2. 0.6175, we get 2. We divide by 0.6175, we get 6. So now we have a cleaned up version, which is calcium 1, H2, C2O6. But I propose to you what this compound is this, and can you name that? We just did this last chapter. I hope you're saying this is calcium, either hydrogen carbonate or bicarbonate. Alright, let's recap this. What's our sequence? 1. Assume you have 100 grams of the compound. To convert that to grams of each element. Divide by the molar masses to get into moles. Once you're in your moles, you now have the ratio. You have a rough formula up here that you can clean up by dividing by the smallest one to return the empirical formula. By mass analysis, you have derived the whole number ratios of the elements. Let me do one more example and then you take it from